In this circuit, we have a capacitor that has an initial charge. And the switch is closed at some time. And so the charges are going to want to move around through the inductor and back around to the negative side or the other side of the capacitor. And so as this charge moves and forms a current, the inductor is going to resist that change. It's going to build up a magnetic field. And once the capacitor has all of its current, all of its charge switched to plates, then I'm going to have the positive charges over here, and I'm going to have the negative charges on the other side. And now the inductor is going to lose its magnetic charge. It's going to destroy itself, and my current is going to change directions because of the capacitor. So now, once the capacitor's current starts flowing, now I'm going to build up another magnetic field in the inductor. And that charge is going to move, and once the charges get off of the capacitor, the inductor is going to kick in, and then as the magnetic field collapses, it's going to push the charges in the opposite direction, and then it's going to be depleted, the magnetic field. And now the capacitor goes back to positive on the left, negative on the right, and it's going to go in the opposite direction. So we have this oscillation back and forth. So this becomes the electric version of a spring, an oscillating spring, or pendulum. And we'll find that the equations are very similar to those. So we can write the equation as the voltage of the capacitor plus the inductance times the derivative of the current, and that's got to be equal to 0. Remember, this is because of Lenz's law. And now the voltage of the capacitor is just Q divided by C. And the current is the derivative of the charge. So I'm going to have d dt of dq function of t dt. And that just gives me, I'm going to divide through by L and rearrange my terms here. The derivative of derivative is second order derivative of charge with respect to time over dt squared plus q divided by, or let's see, divided by L, LC is equal to 0. And this form of the equation, we remember that we had a solution Q function of t is equal to Q naught cosine of omega t plus phi. very much like we had for the spring. And if I put this equation back into my derivative, I'm going to have negative omega squared plus 1 over LC times Q naught times a cosine of omega t plus phi, and that's going to have to equal 0. So remember, just put this equation back in, do the double derivative, and you'll be able to get to this point. Now, Q naught's a constant, so it's really not going to do anything. Cosine changes all the time, and I'm looking for something that equals 0. And the only way that it will equal 0 is if this term with omega squared, negative omega squared plus LC, and I can solve that, and I get omega is equal to 1 over square root of L times C, and I'm going to have a J with this actually. It's going to be imaginary. And that means that our frequency is going to equal this value also. So this equation is general. It's not going to, require a lot of variables here. So we have a lot of constants. And the current as a function of t is equal to negative q function of t over dt, and this negative is because the current is reducing, and that's going to be equal to omega q naught sine omega t plus phi. And our maximum current is equal to omega times q naught, and that's just equal to q naught over the square root of LC. So this is the way we derive what we call an oscillating circuit, an astable oscillating circuit that has a specific frequency that we can choose by placing specific values of inductance and capacitance together. So we'll look at an example in the next video.